Hi, I'm Leon Heitens, and in this video you will learn how to draw the sine function based off the unit circle, and how we will go from the standard sine function to the general sine function. We will also make you understand this function by looking at the different parameters. In the end, we will make an exercise to finish this subject. The sine function is taught in the third cycle of the general secondary education, in chapter of trigonometric functions. The graph of the sine function can be based off the unit circle. By now, the unit circle should already be taught, but I'm going to repeat it with you. The circle has a radius of 1, centered at the origin. To make our applet clearer, we move the center of our circle to -1, 0. When we're working in a unit circle, we use radians for measuring angles. An arc of a circle with the same length at the radians of that circle subtends an angle of 1 radian. The circumference subtends an angle of 2 pi radians. What does this circle have to do with the sine? In the unit circle, we can see the value of the sine on the y-axis. For example, if I want to know the sine for an angle of 30 degrees or pi divided by 6 radians, I have to project that point perpendicular to the y-axis. We call this point P. As you can see, the sine of pi divided by 6 equals 0.5. What does this have to do with the graph of the sine function? In the coordinate system, the x-axis shows the size of the angle in radians. The y-axis shows the value of the corresponding sine. I am now going to put point P from the example in the coordinate system. We can see that the value of the sine is shown in the coordinate system. We can do this for every other angle in the unit circle. If we do this for every angle of the unit circle, we become the graph of the sine function. On this graph, we can see the corresponding sine value for every possible angle size. In this applet, we can only see angle sizes up to 360 degrees, but the angle sizes in a unit circle can go from -infinite to infinite. For example, an angle of 390 degrees has the same sine as an angle of 30 degrees. This is shown by the blue function, the sine function. At last, we are going to draw this function together using our calculator. We can influence the function fx equals sine x by using different parameters. The first parameter is the amplitude. The amplitude is the peak deviation of the function from 0. In this case, the x-axis. The amplitude for the function fx equals sine x equals 1. If we multiply sine x by 3, we become fx equals 3 multiplied sine x. We can see that the function has been vertically stretched with factor 3 in comparison to the original function. The peak deviation, the amplitude, has changed. In the newly formed function, the amplitude equals 3. In general, we can multiply the sine by a. This gives us fx equals a multiplied sine x, with a as a parameter for the amplitude. The period is the second parameter. A period is the smallest possible interval of a graph of a function. After this interval, the graph will repeat itself. In this function, fx equals sine x, the period or angular frequency equals 2 pi, about 6.28. This is a circumference of the unit circle. If we would multiply x by 2, we would become the function fx equals sine 2x. We can see that this function has been horizontally stretched with a factor 1 divided by 2 in comparison to the original function. In the newly formed function, the period equals pi. In general, we can multiply x by b. This gives us fx equals sine b multiplied x, with b as a parameter for horizontal stretch, and the period 2 pi divided by p. Our third parameter is horizontal shift. The parameter for horizontal shift is c. In general, we become the function fx is sine x minus c. Beware of the minus sign. For example, if we add 5 to x, we become fx is sine x plus 5. Here our c is negative 5. We see that our graph goes to the left because the c is negative. In another example, if we subtract 2 from x, we become the function fx is sine x minus 2. Our c is positive, so our graph goes to the right. The last parameter is vertical shift. The function fx equals sine x still passes through the origin. If we subtract 2 from sine x, we become the function fx equals sine x minus 2. We see that the graph shifted downwards by 2 units. In general, we can add d to the sign. This gives us fx equals sine x plus d, with d as a parameter for vertical shift. If we combine all these parameters into one function, we get the general sine function. Fx equals a sine b multiplied x minus c plus d. At last we make a short exercise on the topics we saw today. The exercise goes as follows. Explain which transformations on the basic sine function have to take place to get the following function. Also, give the equilibrium position, period and amplitude of the new function. We are going to start with the first part of the exercise, explaining the transformations on the basic sine function. First, we are going to write our basic sine function. Oops. Like that. Alright. The basic sine function is fx equals sine x. In the function given, we can recognize our parameters. The first one, the 2, is the amplitude, which was an a in the general sine function. Then we have our b for the horizontal stretch. We have the c for horizontal shift, and then d for vertical shift. Alright, so in these types of exercises, the order in which place we implement the parameters is important. For example, if we first implement the b parameter, or horizontal stretch, we have something like this. Fx equals sine 3 multiplied x. Now, if we then implement the c parameter, our horizontal shift, we have something like this. fx sine 3x plus 3 divided by 2. And what we see, sine 3x plus 3 divided by 2 isn't equal to sine 3 isn't equal to this. So we know for sure that that the c parameter comes first, and that is our horizontal shift. So we get a function like this, sine x plus 3 divided by 2. Now, we know in the general sine function there is a minus there. So the c in this example is minus 3 divided by 2. This is important for our explanation. So we made this from our general, for the standard sine function going to this, we implemented a horizontal shift by 3 divided by 2 units to the left, because our c is negative. So I'm gonna write this down. A horizontal shift with 3 divided by 2 units to the left. That's important. Alright. Now, the next one is can be the b parameter for our horizontal stretch. So we have fx is our b is 3, so it's sine 3 multiplied x plus 3 divided by 2. So, and what's happened here? It's a it's a horizontal stretch, with a factor 1 divided by 3. And why is it 1 divided by 3? Because if we multiply with a number bigger than 1, our period will become smaller. So it's not stretching, it's actually going smaller. So we multiply it with a factor 1/3. Next, we are going to implement the amplitude. That's 2, that's easy. So it's 2 sine 3x plus 3, like this. And what's happened here, our vertical stretch, we vertically stretched our sine function with a factor 2, like this. And then at last, our vertical shift, the d is here -4, so we're gonna write this down. -4. And what happened here? A vertical shift with with 4 units down, because it's negative. So that's how we become the function, the given function. the second part of this exercise, we need to find the equilibrium position, the period, and the amplitude. But first, the equilibrium. So, we know for the standard sine function that our equilibrium is 0. Now, our function has vertically shifted with 4 units down. We did this here. So what this means is that our equilibrium is also 4 units down, so it's -4. Then, next, the amplitude. That's an easy one because we can just find it in our function, and that's the 2. So it's 2, and then at last the period. And this we can find it with the formula to find the period, and that is 2 pi divided by our parameter b. And that in this function it's 3. So we get 2 pi divided by 3. And that's how we solve this exercise. And this was the video about the sine function.